So thank you all for participating in the Engineering Day and coming to the College of Engineering and particularly Department of Civil and Environmental Engineering talk. And what I am doing right now is I narrow down my topic a little bit so it has a better focus. So what I did is instead of just talking about the entire resilient city topic, and I narrowed down it to disaster resilient, and that is what it's actually about. And the key point I'm going to emphasize today is about the damage assessment and what we call it the damage inference. Later, I will explain the difference between assessment and inference. So first, before we start, we would like to know actually what is the definition of resiliency. I think you have heard that in different places, and of course in different track, it has different definition. But in general, it means the ability to respond or recovery from a crisis and from disruptive process. And then if you think about the entire government or the entire society that we face, we have a lot of issues that we are facing, and that can be included in the social economic ones, including the crime rate and the diversities and the inequalities. And also if we are working on the engineering side and we are worried about the security and the safety of our environment under natural hazard. And then such natural hazard as we faced in Utah is earthquake and other places on the coastal area that can be flood and hurricanes. So that comes to the definition of disaster resiliency of region and city. So that is again similar to resiliency in the general definition. The disaster resiliency is talking about the individuals, communities, and organizations to adapt and recover from the hazard, and in the both short term and on the long term side. So then the question is, what really happened after a hazard? So I'm moving the participant view to another screen so we don't interrupt with the presentation. So as we still remember our experience after the March earthquake, what happened is after the earthquake, I was thinking about what I'm going to do next. And basically, we are thinking about a decision that is involving the decision. And then when we try to find out if we are going to move out and find a better shelter place, there involves a lot of concerns is whether our place is safe or not, and is the shelter safer or not. And then the question is who is going to tell us which shelter is a better, safer choice. And also there involves other social economy, and also specifically for the pandemic and the COVID-19, we have other concerns beyond the safety. But if we're talking about a general situation after natural hazard, and then on the regional level, on the city level, we are going to consider about the priority for rescuing effort, and we are considering maintaining the functionality of health services, and then we are going to provide housing solutions for people who felt their place are not safe. And then we wanted to maintain the functionality of our infrastructure system, which is the transportation, the electrical power system, and also the communication, which is our cell phone and Wi-Fi. And then other things, more little bit long term is we want to decide how to recover fully back to the normal state. So same thing as what we are trying to determine on the structure on our individual household side is we are trying to think if the place is safe or not safe. And that is the first immediate information that we need to have. So this directly links us to a consideration of damage assessment. So under this umbrella, we are linking the damage assessment or damage prediction as the first step of the solution to maintain the city resiliency after a natural hazard. So under this umbrella, this is the outline of today's topic. So the first thing I want just to briefly talk how earthquake and damage formed in a region. And then I wanted to briefly talked about the state-of-the-art damage assessment method. How is the researcher and the government are currently doing for really understanding what is happening, and that is go back to the immediate information what we want. And then we come up with an interesting idea, which is try to use limited data that we have on our hand, and is it possible to predict a more accurate mapping of the distribution of damage in a region after hazard. So we proposed an interesting idea, but at the same time we raised several key questions. And then the fourth part, which is the bulky research findings we have in our group, which is the framework, that is a damage assessment framework. So I will emphasize on that too. So at the end, I will give some findings and the conclusions for you to take away. So the first thing is about the development of earthquake and earthquake damage. And I think because we are in Utah, I think we are not totally unfamiliar with earthquake formulation and other things. But what it happened is there is a fault, and then there is a fault rupture happened. And then the fault rupture will actually release energy. And then the energy is going to populate through the entire region. And then our soil, our ground is working like a filter. So if you don't know what the filter is, if this does not sound familiar to you, and think about the noise cancellation headset that you are using or you heard of. And what it does is the noise on the other side cannot come in. That is because it filtered out the unnecessary noise other than your voice or other than the sound that you want to hear. So that is the consideration of filter, and how it works depends on the frequency of the signal, and it gets either amplified or reduced. So after all, based on this filter effect, and also energy will attenuate, it will dissipate at the end. So with those two effects, you are going to form a map of earthquake intensity. And the center is what we call the level of the severity of the earthquake, but you will see the color actually reduces when it expands. And then at each individual location, if you have a sensor, what called the seismology sensor, and you can actually pick up the record of the earthquake waves. And this is some examples of the velocity of earthquake at one certain locations. And this is just a view. So it looks very similar as your voice, and because both of them are signals, and you can use the time and frequency component to explain or to describe the signals in the ground. And that is also what is called ground motion. So there is a list of different key parameters that earthquake engineers has been studied for years and identified. So they are all related to the, for example, peak ground acceleration. That means the maximum ground acceleration in your signal. And then the period is just the dominant frequency in the signal. And other things are either related to acceleration, which is the shaking, and or the movement, which means how much the ground is actually moved. And the velocity is just the derivative of the movement or the integration of acceleration. So you know that in your physics. So after knowing what happened to the ground, the next concern is what happened to our structures, because you need to have something showing your structure to consider it is damaged or not. So that the first part after here, we talked about the earthquake deformation or earthquake development, and then we will move on to the damage development. So we know that the force and the reaction relationship, if you push on your hand will feel something. And then if someone hits you, you will feel pain. And then someone hit you really severe, and then you will get hurt, and maybe you broke your arm or broken your leg, but or you hit on some other trees, that also the same thing. So it's the same mentality that your structure under a certain severe load, that load is what the ground motion does to the structure. It will deform and it will get damaged. So we have the relationship of the ground motion to our property of the structure. For example, property of the structure is to explain how strong the structure is. And then the stronger the structure is, and the less it will get affected by earthquake. But then the strong definition is very broad. It's not like if you are more harder the structure is, you can actually survive. It is related to the dynamical property of the structure, which is the period or the frequency. And think about what you have heard about the bridge is going to under resonant if you are working with a certain frequency that is coincide with the frequency designed for structure. And that is what happened in the early war time. And that story, I think, is not unfamiliar to you. So this is some taste of what we describe about the structure. And then after the combination of the input and our structural property, you will have see damage formed. And you can see this figure at the lower level because the deformation or the displacement, that means the first story moved rather than how the column on the first level can sustain. And then you can see the damage. So at the end, the damage is a function of the structural response. And actually, I have the page, the figure, I think they're on top of each other. So this is the X. X is the outcome of this entire process. Okay, see if I can go to this this page anymore.
You're muted.
Yes, yeah, okay, sorry. So we were up to here. At the end, we are trying to understand how to identify if the building is damaged or not. So we have a lot of different design code, and from the design code, we know, okay, these are the critical parameters, such as how much the building has been shaped, and we know because of that, the facade, like the windows, cannot survive if you have too much shake. And then because of the column have been drift a lot, that means as what you saw earlier in this page, the first story just going to collapse. And then there are other observations such as if it collapsed or not, it's very obvious that we can consider that as damage labels. So overall, this entire framework or this entire process tells us, okay, the starting of the occur in the fault rupture and to the final process that the building has been showing damage. So we know this is how that works. And then let's take a look on what is the damage assessment method that is currently implemented. So we go back to this figure, and then we are trying to identify what different researchers have used. So because we are civil engineers, or we are engineers, and we most concerned about the structural performance once we know the ground motion, because this part, the ground motion, the distribution or the transmission of energy into the region is more like the geological studies. So on the structural side, we are stick with the structural performance. So there is the first study, or the most common study. This is vulnerability analysis. So that is a statistical description of how building is going to perform under earthquake. And that is based on tons of simulation of different buildings. So what this figure actually tells us is x-axis is earthquake intensity of a specific building. And if the intensity of earthquake at the given location is moving to more on the x-axis, and then we are going to see higher probability of occurrence when the damage on different levels. So for example, if you are on the higher level or lower level of intensity, and you are going to see it's more likely to be slightly damaged, and but it does not likely to be complete collapse. But when you're moving to the x-axis, we have more stronger motion, and that means you have 100% possibility to have it to damage it as a slight damage, and it have slightly less probability to be moderate and slightly less probability to be extensive and slightly less probability to be complete failure. So using this figure, and if you plug in the ground motion at each location, and then you can come up with the damage status. And this is purely based on simulation and also the knowledge of the ground motion after a specific event. So this is the example that is done by the USGS, the geography survey. So what we have is we have the ground motion recordings, and then we form up this map. And then after we have this map, we plug in the structural vulnerability function, and also including some other place, location, and time parameters. And we can have a distribution of damage and the fatalities and other parameters that we felt important to look at because due to the decision-making purpose. And so on the green side, this is overlapping with the previous figure. Green is the slight damage, and red is a severe or complete collapse, and then the yellow and orange is in the middle. So with this, we can have a distribution of damage as a bulk statistical numbers. But the point of this method is, where the limitation of this method is, we don't actually leverage any observations from the field about damage to help us to update our model, because any model has limitations, and you need to know specifically details of the models so it can work perfectly. And this result can yield errors or discrepancy about what really happened. And then the second, more high resolution. By high resolution, we mean more case by case, is based on the physical-based simulation. And that is, as you can see from this figure, for each individual building in the region, you can create a simulation model for this specific building. And then you plug in the exact earthquake ground motion at the foundation of this building. And then we can come up with the entire response history of the building. And the benefit you have is you can have as many parameter or as many indicator of the building as you want during this analysis. You can see that each level or each story level, what the damage, what is the displacement looks like, what is the acceleration looks like, and what it does it yield. Yield means damage. Does it damage at each level or not? So very fine resolution solutions. But the limitation is you cannot have accurate model one by one. It requires a lot of analysis and modeling, and also data acquisition to get the correct information you want for each building. So it's, and also it is very computational expensive. So these are focused on the structural response side. That means we know what happened in our region, and we know some property of our structure, and we can predict the damage. And another side is on the data side. The data side means we observe what had happened, and then we record it. So the common two ways of doing that, or the most state-of-the-art two way of doing that, is one is remote sensing. So remote sensing is when we have the remote sensing is what happened when we have the ground information and from the satellite, and from before and after. We can compare before the earthquake or before the hazard and after the hazard. We can come up with a classifier if this building is being damaged or not. And at the end, it will just format the map of what this damage is predicted. And the benefit is it is fast. It can be done like really quick because you just use image processing. But what the limitation is, it cannot distinguish minor damage because you are only looking at the exterior of building, and in most importantly, you are only looking from a very far away distance, and that means the small displacement or drift of the building cannot really be well captured. So it's able to capture the collapse accurately, but not anything in the middle. And also, anything about the building property and the ground motion is not taken into account before you do this analysis. And the last one is what is still being done is about a reconnaissance survey. And after earthquake in Nepal, in Turkey, and they send out, and also especially the severe earthquakes, they send out a group of teams, and they have a checklist about what they're supposed to look at, and come from the comprehensive list, and they made some decision about the situation of the buildings. So we consider this approach to be most accurate, and still it only provides us a case-by-case result, and it does not give us anything by buildings that we don't inspect. And also, so that means covering the entire region, even just covering the damaged building, it requires about 1 year to finish the survey if the damage is severe. So that does not help us to boost the decision-making process. So what we want to do is we wanted to come up with a list of methods that can actually estimate the damage level of all buildings. And also we wanted to be practical and cheap. And also we wanted to conduct it rapidly after an earthquake. So the time is really sensitive. And then we want some high resolution, not just damage, not damage result, or collapse or no collapse result. And we want it to be adaptable to any event and any region. We don't need to run intensively simulation for that. And also we wanted to take account both real world hazard and damage information at the same time. So with this mentality, we are going to see the ideas that we have formed up and also the associated key research questions. So this is the same figure that I've showed earlier in the slides about the earthquake and the damage development. And though we can see, if we talked about function point of view, the ground motion, which is this time history, or this wave, is a function of soil condition, because soil is working as a filter, and location, because it depends on how far you are away from the epicenter of the earthquake. So that is related to energy attenuation, and also other earthquake parameter that is from the source. And then we know that our response X is a function of your ground motion and other building properties. And MCK, M is mass, K is stiffness. Stiffness is trying to describe how stiff your building is. Mass is, of course, trying to describe how heavily weighted your building is. And then your response is a function of all these parameters. And then if we substitute the F into the figure, then we know this actually is a function of soil condition, earthquake parameter, and the location. And then your building damage status is a function of your building response. Response means the displacement, and the building damage is related directly to the displacement and acceleration. But if we plug in all the parameters that we have in this figure, is H is a function of all the parameters of your building and ground motion and the soil. So this is what we have come up with, a more high-level general function, that the damage of individual building is a function of all these parameters that I just mentioned. And is it possible we approximate this function using learning? We're using machine learning, because machine learning, what machine learning, the idea is, it is try to learn an unknown relationship. If we just directly pick the damage and all these parameters that we have as a function, we felt that machine learning may help us to really approximate or infer the relationship of this function. So this is the list of input and output we have, and that goes back to the formulation of damage in the earthquake. And because we feel that the building under in the similar region, for example, Salt Lake City, it is designed under the same building code, and it is designed at same different age. It has different. It has similar attributes. If you look at the building in 1970, it almost looked similar in a certain way, and etc. So we have this assumption that all these similarity can help us to maintain more consistent function. So with this idea, we proposed the learning or the inference of using labels such as the damage level as the output or as the observations, and the input are the building height, building area, year of build, and number of stories, and other building properties, and also including all the ground motion measurement that we have at different locations. So that will fulfill us the previous function that we have, which is SD, damage, is related to soil, location, and some implicit measure of building properties, such as stories. And stories can impact our stiffness, which is determine how hard or how stiff your building is. And also stories can help us understand or predict what is the weight our building more likely to look like. So under that, we move on to the input and the output relationship. And so we used all the building properties that we can think of, and also we use all the earthquake properties that we can think of, and we even include other properties of waves that is not in our traditional earthquake engineering field. It's in the signal processing field, because we mentioned that the earthquake looks more like voice, right? So anything that we felt helpful in the signal processing, we felt maybe we can put it into the earthquake study. And then we use other measurement about damage as our observations and the prediction. So the next figure tells us how machine learning in earthquake engineering work. In our particular interest, how does it work? Because machine learning is trying to predict the input-output pair. And then we need to know what our input and how we acquire our input for this problem. So for input side, before the event, we assume we have the building information that related to the building property that we have. For example, building height, area, year of build, number of stories, type of buildings. Is it an office? Is it a hospital? Is it a residency place? And then is it a concrete structural type? Is it a concrete building? Is it a steel building? So we assume all those information are pre-acquired. And then during or immediately after the earthquake, we have a seismology sensor at different locations. So we track these sensors, and then we send out the reconnaissance team to observe the building damage. And from earlier, the ground motion and the building information is considered as input, which is a feature in data science. And then building damage inspection is considered to be the output, also named the label in our training. So we have a core of machine learning model, which is trying to learn the relationship of what we have observed. And after the model has been trained efficiently, and we just use this model to predict what happened for the rest of the area. And you can see the damage level of other buildings can be assigned, and we hope that can be a higher resolution level rather than just damage or non-damage. Okay, so with this picture, the question is if it will work or not. And then if it works, what are the key steps to make it work better? So to have this, to answer the first question, would it work? So we need to identify what machine learning model we can use to predict the nonlinear relationship between the damage and all the other inputs. And then if it works, how do we optimize this model, particularly for our usage? We have lots of different input, all of them informative. Do we need to keep all of them? Because the more input you have in a machine learning model, the more likely it will overfit. Overfit means it will give you the accurate result no matter what, but it does not reflect the true intrinsic relationship between input and output. So the idea is to minimum using the necessary input in your learning model, we can have a better confidence in the outcome. So how do we identify the variables that are most influential in this process? And then the last thing is about the practicality of this research, where we want it to be cheap. Cheap means we wanted to use minimum labor, minimum effort to acquire our output or to acquire our observations. So that means, is there a better way that we can assign the observations so we can have the best accuracy of the model? So our research trying to answer the 4 questions. So we move on to the next session, which is about the Gaussian process regression-based post-hazard regional building damage inference framework. Okay, this is a long sentence. So the first one is about GPR. GPR we will talk about as the main tool, main model we want to use, and the rest is just damage inference. So basically, we're using a machine learning tool to predict the damage or to in the field, in the region. So why do we choose the learning model to be a Gaussian process regression? And this is a complex mathematical process, but the idea is similar to what you may heard as linear regression. It is the nonlinear generalization of linear regression. And what you can see is this is a process of just a one-dimensional function. And with more data you acquire along the way, and then the Gaussian process, which is the average of the line, is more close to a true function, which is the one that is dashed. And it has the capability to predict the probability or the uncertainty of the accuracy of your observation. That is really beneficial to us because we wanted to know the accuracy of the damage prediction. At the same time, we want to evaluate, is our prediction confident? So that means the higher uncertainty, that means we are more uncertain about the accuracy at a given point. And the lower uncertainty, that means we are mostly certain about the level of damage we predicted for each building. So with these ideas, we move on to the next question. So how do we maintain the best performance, and how do we keep the minimum data sets that can actually, minimum variable that can provide a good model? And then to save some effort, I just list several different functions that is key to the Gaussian process regression, and that is called covariance function. You don't have to understand in detail what they are. They are just a bunch of families that you used in the Gaussian process regression and to create different models. And then you can see the smoothness from different family of model is different. And for the green one, this is RQ, that is the rational quadratic, where the quadratic function, they yield the most smoothness between different points. And then the more you move on from here, and you will see less the continuity is. So this is the distinction of those functions, and we use them just for reference. So what we did is we select a bunch of covariance function, and we wanted to identify the feature, which is our input parameter for buildings and for ground motion. We wanted to identify which one is most informative, and then we are trying to optimize those functions, or covariance functions. At the end, it can predict the performance. And what we see earlier in the convergence of our Gaussian process regression prediction to the true label is where the hyperparameter is optimized to the true function that we want to predict. Okay, so under these levels, we go back to this slice, and this is all the information we wanted to collect. For example, the building features and the ground earthquake features or building information and earthquake informations, we have it for all the buildings that we wanted to measure and predict. And for the building damage labels, we only have it for the buildings that we wanted to, we treat as observations. And then we need to have some test bed to evaluate our result about. So eventually, this is what we have is we have 20,000 buildings in a region, and then we have 11 input from structure, and we have 20 input from earthquake, and we have totally 31 inputs, and then we have 5 output from the labels, and this is the entire space of our study. And what we have for the test bed, it is done by a simulation platform, and this test bed are provided by Sim Center in Berkeley, and they simulate 2 scenarios, one in San Francisco and one in Anchorage, and they have different magnitude and epicenter. And we can see this is the ground motion maps for different for both regions, and that is the earthquake part. And for building part, they simulated the building response similar as what I showed earlier from the physical based analysis. Basically, you have each model for the buildings in the region, and this is San Francisco, and this is Northridge, and you can see the height of the building in this region, and also the year of build in the different colors and how it's distributed. And what you can find out is actually, of course, the San Francisco area has more high-rise building than Anchorage, so this is very distinctive in the figure. And in the test bed, we have 184K buildings. That means 0.1 million of buildings simulated. And in this case, we have about 20K buildings simulated. And then we come up with different performance assessment formulas. That is try to criticize or evaluate the performance of our machine learning model or the GPR model. So you can see the SMSE, that is the mean standard mean square error, and also correlation coefficient, that is also another indicator to identify the error. And then we have relative error and relative difference. So they are all set of different measurements for us to evaluate the performance. And this list, you don't need to worry about the details of what they are. You just need to see the IDs. It's about to select the covariance function. As I mentioned, the covariance function in the GPR is differentiate the performance of one model to the other. So we have come up about 16 models under the GPR umbrella, and we want to see which one performs the best. So using the different test bed, and we are trying to see the error and with the data, or with the different covariance model, and all of them are including as the 16. So you can see distinctively COV 8 and the COV 15 works the best, and the D1, D2, D3, D4, and D5 just different damage label. We have 5 damage label, and we found out COV 8 and COV 15 are both on the RQ family, that is rational quadratic family. And then one thing is the other one is more complex, RQ ARD, and the other one is linear ARD. So combine them together. Even maybe COV 15 works slightly better, but because the model itself is more complex, so we decided to go ahead and with the COV 8 or RQARD model at the end. So that is one of the research questions: how to optimize our model so it works better. So we choose the covariance function, that is RQARD, so it has the best performance among all of the models. And then the next thing is about to identify the minimum number of inputs we want to acquire to avoid overfitting. And then we can see this is the building and the earthquake feature combination table. And we are plotting the correlation between each one. And what you can see is the higher correlation means the darker the area. That means the two label are more two features are more similar. That means they basically tell you the same thing. And of course, you can see the diagonal, which is B1 to itself. It is the same thing, so it has 100% correlation. But if you look at 93, or if you look at B2 and then B4, that means our building has two parameters that is give us the same idea, which is the mass and the area of building. Because when you calculate the mass of building, it's basically a constant density times the area and times the thickness. So they are linear related, and that means they give you the same idea. And also floor area and the initial stiffness, and also number of stories and natural period. And for these ones, we have peak ground acceleration and other parameters that gives us a similar description of the ground motion. And that is why they are higher value in the correlation. So our idea is maybe we can exclude the redundant parameter in the learning, so our learning model is more concise. So under this idea, we come up with a different measure of the importance of features. And then we can see this E8, which is the ground motion property number 8, has smaller values. And that means the smaller length scales indicate the higher influence. And that means even among the similar parameter. Yes, let me take a look. Okay, okay. I thought I have for 1 hour. Okay, so I will wrap up a little bit quickly. So our idea is we try to use this feature table and to come up with the best feature combinations. And then we find out actually the full set feature and only earthquake ground motion, only building features does not provide us actually the best what we can. So we come up with the best practical feature set, which is more economic to acquire. And then after that, the building features and earthquake features are limited to 12 at the end. So with this precise set, we are able to just get a good result. So at the end, I will just go through really quickly. So how do we actually use a sampling methodology to get the good results? So I'll just skip the introduction about the sampling technique. This is based on K clustering. So basically we divide the region into clusters, and it relates the distance between one set to another. And we find out the cluster center of those data. So we found out actually if we acquire the building from the largest cluster to the smaller cluster, and then we can have actually very impactful result in terms of prediction. And if, for example, if you're only using C1, that is the cluster 1 with the largest cluster group, and then we can have actually 60% of the entire region predicted accurately. And then the findings is, if we're using this cluster method and compare with not using the cluster method, just a random selection, and we're using 200 data sets, can actually outbeat the 500 data set result. That means we can actually improve our accuracy by 2.5, the factor of 2.5. So this is just some general result we got to prove our hypothesis. And then in the end, this figure, I think, should be interesting to look at. This is the damage we predicted, and we compared with the damage that is simulated from the test bed. And you can see the distribution of different labels: acceleration, drift, displacement, and collapse probability are all actually capturing the distribution. So also the same thing for anchorage. So in the general conclusion, we come up with the hypothesis that we use machine learning and real measured data from the field and also from the ground motion, we can predict the damage accurately. And we used the Gaussian process regression as a learning algorithm as it predict the nonlinear relationship and also provide us uncertainty measure. And also we identified a different covariance function and reduced the feature table. And at the end, using a cluster-based representative sampling, we can, using smaller number of observations, but predict a very high accuracy of result. So I went a little bit over time and hope that is still okay. And of course, I'm welcome for the questions and if we have any. So these are the acknowledgement. The work is done by my PhD student. And okay, so thanks for participating. And so is there any questions that I can take? Anything from the audience? So let's see the chat. Okay, so yeah, I'm very happy to present this interesting idea. At least I find it interesting, and hopefully, I know this is a little bit beyond what you expect for civil engineering, maybe not, but I think you may have this as extra knowledge when you're trying to determine which college or which department that you want to apply for the undergrad study. And hope all the success of your study and your application, and everybody stay safe in this difficult situation. Okay, thank you.
Bye, thank you.
Thank you.